All right, the last topic in this course is cosmology. Cosmology is the study of the origin and evolution of the universe, and it's amazing that we can actually say that that is a legitimate science. For most of human history, it was the realm of philosophy and theology, and yet now we have evidence that we actually know very precisely how the universe and when the universe came to be. Let's go back a couple of lectures, and we talked about the Hubble law. Remember, the Hubble law said that the speed at which velocities seem to be moving away from us was proportional to their distance. And one thing we didn't say about that, we were using that as a good way to figure out the distances to distant galaxies. But there's a much more important implication of that. And the important implication of that is that it implies that the universe is expanding. Let's take a look at this. Let's say we're here on the Milky Way, inside the Milky Way, somewhere here, and a certain distance away from us we have Galaxy 1, and twice as far away from us we have Galaxy 2. So when we look at Galaxy 1, it's moving away from us at a certain velocity, v, but Galaxy 2 is moving away from Galaxy 1 also with a certain velocity, v. So when we look at Galaxy 2, it's moving away from the Milky Way at twice the velocity that Galaxy 1 is. And that's basically the Hubble expansion. Hubble expansion says that the farther away you look, the speed at which a galaxy is moving away from you is proportional to the distance. And galaxies that are twice as far away will move away from you twice as fast. A galaxy 10 times far away will move away 10 times as fast, and so on and so forth. Now, that may, at first glance, suggest that the Milky Way is the center of the universe. That is not the case. Okay, in fact, there is no center to the expansion. Think of it this way. Think of a group of children, a class full of, say, third graders, and you place them equally spaced on a playground, and you tell the third graders to immediately run away very fast from every other person on the playground. Well, that's impossible, because no matter which direction they run, they're going to be running toward one of their classmates. The only way you can make everyone seem to expand away from everyone else is if the playground was made of, say, a stretchy elastic, and instead of telling the children to run, you stretch the playground, the rubberized surface of the playground in all directions. And in that sense, what happens is the rubberized surface gets larger, stretches in between each child, and each child sees that the farther away the other classmate is from them, the faster they will seem to be going away from them. So the same thing is true of the universe. There's no center of the expansion. Each galaxy is increasing its distance from every other. Each galaxy thinks or seems that it's at the expansion center. But what's actually happening is the space between the galaxies is increasing, kind of like that rubberized playground. The galaxies that are initially far apart seem to be separating at a faster velocity. So that's why the galaxies that are 2 times as far away will move away twice as fast, because there's twice as much space expanding in between. Another way of thinking about it is the galaxies, when we look at the Hubble expansion, when we look at the redshift of galaxies caused by the Hubble expansion, the galaxies aren't really moving away from us through space. They are moving away from us with space. They are embedded with space. Now, they also have their own peculiar velocity, and that's actually a scientific term. Peculiar doesn't mean just strange. It means that it's the velocity relative to empty space, or relative to the average of say, the cluster. But they are moving with space. Another good analogy is to think of raisins and an expanding loaf of raisin bread. Okay, when you put the loaf of raisin bread in, and I did not make this drawing, it's not a very good drawing, but when you put the dough in, and you have the raisins scattered about, probably not this regularly, but you put the raisins in there, and the loaf will expand because the bread in between the raisins will expand. And so, for example, raisin 3 will seem to be going away from raisin 1 twice as fast as raisin 2. Or, if you're on raisin 4, you will see raisin 3 going this way, and raisin 5 going that way about the same speed. But raisin 2 will be going twice as fast, and raisin 6 will be going twice as fast in the opposite direction. And then raisin 1 will be going 3 times as fast as raisin 3, and so on and so forth, mainly because the space in between, or the bread in between in this case, is expanding. So you can think of the space in between galaxies, or actually in between clusters of galaxies, as expanding very similar to the way the bread in this loaf of expanding raisin bread does. So the galaxies are not moving through space, they are moving with space, like the raisins in the expanding loaf of raisin bread. One big difference is that the universe has no crust. Okay, as far as we know, there is no edge to the universe. There's no sign that you come upon that says universe ends here. And it's a little complicated to understand. We probably won't go into the details of that. But it's sort of like the fact that you can keep walking anywhere on Earth and not come to an edge. I mean, you might come to an ocean, but then you can sail on the ocean, and you will never fall off the edge. Okay, as people used to think long ago when they thought that the Earth was flat. Space itself is expanding. And that begs the question, well, what is space? Is it a thing? Well, yes, it does seem to be a thing. But we might not actually get that deeply into that. Okay. Another thing to understand is when we see the redshift from distant galaxies, it is not actually a Doppler shift, it turns out. Okay. The redshift of distant galaxies isn't a redshift caused by the galaxies moving through space. It's caused by the stretching of the wavelength of the photons as space itself expands. So in other words, let's pretend that raisin 6 here is a galaxy and raisin 1 is another galaxy. So when raisin 6 emits a photon, let's say a blue photon toward raisin 1 here, and let's pretend it manages to avoid all the raisins in between. When the photon from raisin 6 is shot across the bread to raisin 1, by the time it gets to raisin 1, the bread has expanded by this much. So basically, a photon that had a very short wavelength, like a blue photon perhaps, would be stretched to a much longer wavelength, let's say like an orange or red photon, by the time it reaches raisin 1. So this redshift that we see is actually caused by the photon's wavelengths being stretched by space itself as it travels millions of light years through the expanding universe. So the cosmological redshift is not caused by the same effect as a Doppler shift, even though the same equation applies to both to find the velocity. Now, one would think, well, that means that if we run the clock of expansion backwards, that means that everything in the universe was all pretty much in the same place, or at least it was all densely packed together at a certain time ago. In fact, that's something we now call the Big Bang Theory, and that is the working theory of the universe. But a few decades ago, that was not well accepted. There were competing theories, and it's instructive to go through these competing theories just to show how science progresses. So only a few decades ago, there were two main theories of the universe that were competing for acceptance. And the one theory, the one that eventually lost, was called the steady state theory. Okay, the steady state theory said basically the universe is eternal. The universe has been in existence forever. It had no beginning, it will have no end. It is pretty much the same it was all the time and will always be. Okay? So it says that the universe should look the same no matter when we are in it and no matter where we are in it, as far as on the largest size scales. Okay? So the universe is unchanging and eternal. Now you might think, well, I already have some evidence against that, and that's the expansion of the universe, because the visible universe now is much larger than it was in the past. Not so fast, says the steady state scientists. Okay, doesn't the Hubble expansion show that the universe is changing? Well, they would say no. Changes due to expansion can be smoothed out if you allow for matter to be created to fill in the gaps. So in other words, if two galaxies are moving apart and they get twice as far apart, a new galaxy will form in between to kind of fill in the gaps and make the average density of the universe the same. And you might say, wait a minute, that's not fair. You didn't tell me where the matter came from. And then the the steady state person would say, well, you didn't tell me where the universe came from in the first place, so we're even. So it's a really interesting philosophical argument. But this was called the expanding steady state theory. And for a while, that seemed to be a pretty good argument to the people who believed in a universe with an absolute beginning. However, there is more evidence that you've already learned against the steady state theory. Okay? The first one, you have to go back to our chapters on stars. And remember we had, even earlier when we talked about the Milky Way galaxy, we said that there were two main populations of stars. Population 2 stars, which were the first generation stars, stars that were made primarily of hydrogen and helium with only trace amounts of heavy elements. And then we had the population 1 stars, which are second, third, and fourth generation stars, which are basically recycled stars. They're mostly hydrogen and helium, but have up to 3% heavy elements, or metals as astronomers call them. And the only way that those heavy elements could have been created, we believe, is in previous stars that existed in the early universe, when the early universe was chemically much more simple, when it was made almost entirely of hydrogen and helium. So, in other words, as time has gone on, the newer stars, the stars that were born more recently, are more enriched with heavy elements. So the universe is sort of evolving chemically from a much simpler state of hydrogen and helium to a more complicated state of hydrogen, helium, and a small percentage of everything else on the periodic table of elements. And just in the last section, we also learned that if you were in the early universe and you looked around in the sky, you would have seen lots and lots of quasars. You would have seen galaxies that had these insanely bright cores shining brightly in the sky. We don't see that now because quasars seem to be a relic of the distant past. So that shows that the universe was once different than it is now. Okay, it is certainly not filled with quasars, whereas when we look far away and our look-back time is close to the beginning of the universe, it showed that the universe was quite different. So this shows the universe has evolved with time. Now, the theory that we now believe is more or less correct is called the Big Bang Theory, which is kind of ironic because the term Big Bang Theory was actually coined as a derogatory label for this theory. It was actually coined by one of the scientists who was supporting the steady state theory, and he thought that it would be a kind of a clever thing to call it, to kind of be a derisive term, but in fact it caught on. People said, "Oh yeah, that's kind of cool. Let's call it the Big Bang Theory," and now there's been a popular sitcom of the same name. But long before that sitcom, there was the Big Bang Theory, and if we run the movie of expansion backwards in time, we would see all the galaxies and stars converge as the space between them gets smaller. Okay, so what that means is that the current observable universe must have exploded, and exploded is kind of a misleading term, but expanded, let's say, perhaps, is maybe a better word than exploded, must have rapidly expanded from an initial high-density state. Now, that doesn't mean that the entire universe was a little blob of material or energy in a pre-existing empty void and then exploded to fill up that void. It was the entire universe, so it still might have been infinite. However, it was smaller. So how do you get a smaller infinity than infinity? That's the question I can't answer. However, the universe we can observe now was probably the size smaller than an atom. We'll go on to this craziness again in the next section.